Black holes are some of the most mysterious objects in the universe. Imagine a place where gravity is so strong, so incredibly powerful, that nothing can escape its grasp. Not even light, the fastest thing we know. These cosmic titans lurk in the darkness of space. They challenge everything we think we know about reality. The universe holds many secrets. Black holes are among the biggest and most profound. They pull everything towards them with an immense, invisible force. Picture yourself drifting through space. You approach a region of pure blackness. It is darker than any night you have ever experienced. You begin to feel an unseen tug, a gentle pull at first, then stronger and stronger still. This invisible force is the black hole's gravity. It is a one-way journey into the unknown. Once you get too close, there is no turning back. This is the sheer power of a black hole. Its gravity dominates everything in its vicinity. Black holes have fascinating origins. They are born from the death of giant stars. Not just any star like our own sun. We are talking about stars that are truly massive. Stars many times bigger than our sun. These colossal stars live very fast lives. They burn through their enormous supplies of fuel very quickly. Their lives are spectacular, shining brightly across the cosmos, but their lifespans are relatively short compared to smaller stars. This sets the stage for an even more spectacular end. When a truly massive star exhausts its nuclear fuel, gravity finally wins the cosmic tug-of-war. The star's core can no longer support itself against the immense gravitational pressure. The core collapses catastrophically. This collapse happens incredibly fast, in mere seconds. The outer layers of the star are violently thrown off into space. This creates a gigantic explosion known as a supernova. A supernova can briefly outshine an entire galaxy. What is left behind is an extremely dense core. If this leftover core is massive enough, about 3 times the mass of our sun or more, nothing can stop its continued collapse. Gravity crushes it down relentlessly. It squeezes all that matter into an infinitely small point. This point of infinite density is called a singularity. At the very heart of every black hole lies the singularity. Take all the immense mass of a collapsed giant star. Now picture all of that material squeezed into a point with absolutely zero volume. This means its density is infinite. Our current laws of physics, including Einstein's theory of general relativity, cannot fully describe what happens at a singularity. It is a place of ultimate mystery and extreme conditions. Surrounding this central singularity is a crucial boundary. This boundary is known as the event horizon. It is the ultimate point of no return. Once any object or even light itself crosses the event horizon, it cannot escape the black hole's pull. It is forever trapped. Think of it like the edge of a cosmic waterfall. Once you go over, there is no coming back upstream. The size of the event horizon, often called the Schwarzschild radius, depends directly on the black hole's mass. More massive black holes have larger event horizons. The great physicist Albert Einstein gave us a revolutionary idea about gravity. He showed us that space and time are not separate, independent entities. Instead, they are interwoven. They form a single, 4-dimensional continuum called space-time. You can think of space-time as the very fabric of the universe. This fabric is not static. It can bend, stretch, and warp. Massive objects like stars and planets cause this fabric to curve. This curvature of space-time is what we experience and perceive as gravity. A black hole is like an incredibly dense, super heavy object placed on that rubber sheet. It creates an extremely deep, almost bottomless well in the fabric of space-time. The space-time around a black hole is stretched and distorted to an immense degree. This extreme warping of the cosmic fabric is what gives black holes their astonishingly strong gravitational pull. It is a place where space-time itself is pushed to its absolute limits. Imagine you are an intrepid astronaut. You decide to take a journey towards a black hole. Let's say you are falling feet first. As you get closer, something very strange would start to happen to your body. The gravitational pull from the black hole would be much stronger on your feet than on your head. This is because your feet are slightly closer to the black hole's center of mass. This difference in gravitational force across your body is called a tidal force. These tidal forces would stretch you out like a piece of spaghetti. This bizarre process is vividly and accurately named spaghettification. This stretching effect would become more and more extreme. Your body would be elongated, becoming incredibly long and thin. Eventually you would be pulled apart, atom by atom. This is certainly not a pleasant thought, but it powerfully illustrates the extreme nature of a black hole's gravitational field. For smaller, stellar mass black holes, this intense spaghettification can happen even before you reach the event horizon. For supermassive black holes, you might cross the event horizon relatively intact, only to be spaghettified closer to the singularity. One of the defining characteristics of black holes is that they are, well, black. They do not emit any light of their own. Light cannot escape their powerful gravity once it crosses the event horizon. This makes them completely invisible to our eyes and telescopes in the traditional sense. So, how do scientists find these elusive objects? It is like trying to find a black cat in a completely dark room. But astronomers and physicists are very clever. They have developed ingenious methods to detect these invisible giants. They look for the profound effects black holes have on their surrounding environment. One primary way to infer the presence of a black hole is by observing the motion of stars. Sometimes astronomers see a star orbiting what appears to be an empty spot in space. The star moves as if it is dancing with an invisible partner. By carefully measuring the star's orbit, its speed, and its period, scientists can calculate the mass of this unseen companion. If the invisible object is very massive, yet very compact and emits no light, it is a strong candidate for being a black hole. Many black holes have been discovered this way. There are many popular myths and misconceptions surrounding black holes. One common idea is that black holes are like cosmic vacuum cleaners. People imagine them roaming through space, aggressively sucking up everything in their path: stars, planets, and entire galaxies. This image, while dramatic, is not entirely accurate. Black holes do have incredibly strong gravity, that is true. But they obey the same fundamental laws of gravity as any other massive object in the universe. They only consume matter that ventures too close, crossing their event horizon. Their gravitational influence, while strong nearby, is not infinite. Imagine if, by some magic, our sun were to suddenly transform into a black hole of the same mass. Earth would continue to orbit this new solar mass black hole. It would follow exactly the same path it does now around the sun. Of course, without the sun's light and heat, life on Earth would freeze and perish, but we wouldn't be gravitationally pulled into the black hole unless we got much, much closer. Another myth is that all black holes are purely destructive forces. Studying black holes is incredibly important for science. They provide us with unique, natural laboratories. These are environments where gravity is unbelievably strong. Our best current theory of gravity, Albert Einstein's general relativity, is pushed to its absolute limits in these extreme conditions. By observing black holes and their effects, we can rigorously test Einstein's theories. We can see if they accurately describe reality under such duress. This helps us refine our fundamental understanding of how the universe works. It helps us build better models of the cosmos. Black holes are essentially pure manifestations of gravity. Gravity is one of the four fundamental forces of nature, yet it remains in many ways the most mysterious. We understand electromagnetism and the nuclear forces quite well at the quantum level, but a complete quantum theory of gravity still eludes us. By studying black holes where gravity reigns supreme, we can gather crucial clues about its deeper nature. Black holes are undeniably captivating cosmic objects. They represent one of the ultimate mysteries of the universe. From their violent births in the explosive deaths of massive stars, to their mind-bending effects on the fabric of space-time. They constantly challenge our intuition and our imagination. They serve as profound reminders of how much we still have to learn about the vast cosmos we inhabit. Black holes are truly one of nature's most extreme and fascinating creations. Their ongoing study is a thrilling journey into the very heart of the unknown. The quest for knowledge about black holes continues with great enthusiasm. Scientists around the world are using increasingly powerful telescopes. They are developing new observational techniques and theoretical models. We have imaged the shadow of a black hole. We have detected the gravitational waves from their mergers. Each new discovery brings us a little closer to understanding these enigmatic objects. Yet, each new finding also tends to raise fresh questions, opening up new avenues for research. This is the very nature of the scientific process.